when we were solving a times a vector is equal to lambda times a vector, right? Which means this is an eigenvalue or characteristic. I usually like to think about those as pairs. It's an eigenvalue vector problem. Now, if you took this and you actually solved it, and so you go ahead and find the eigenvalue vector pairs, and what you found was, like, say, lambda 1 corresponds to, say, x1, and then lambda 2 corresponds to, say, x2, and then you found lambda k corresponds to, say, xk. So you found all these pairs. You found every single one of these. And what they all mean, if I would write it in terms of an equality, each of these mean that a times x1 spits out lambda 1 x1. And a times x2 spits out lambda 2 x2. And a times xk spits out lambda k xk. Now I have these k equations. Well, one of the things you can do with matrices is to collect every one of the equations into one particular symbol. So for example, on everything on the left-hand side, the left sides could be written as one thing. This would be a times, if I would write it horizontal, this would be a times x1, x2, up to xk. Because how does A will distribute, right? It goes through each of those columns. So it's A times the first, A times the second, A times the third, A times the case. That would be all of these left sides. On the other hand, the right sides can also be collected. The right-hand sides, if I look at this, if I have A all times x1, x2, up to xk, and I go ahead and distribute it, that's ax1, that's ax2, up to axk, but I know what each of these are. That's just simply lambda 1 x1, lambda 2 x2, up to lambda k xk, right? So a times each of these x's, the a would distribute, but that would multiply through, and we just get all of our lambdas. But I could actually take this and write this as a matrix operator, which would be x1, x2, xk as a matrix, all times lambda 1, lambda 2, lambda k as a diagonal matrix. Because what this says is it says column 1 times row 1. When we do that, we would just simply get the lambda 1 and all the zeros, and then we get the whole lambda 2 x2. And so this diagonal matrix, when you would multiply it, it'd be x1 times lambda 1, 0, 0, 0, 0, and then it'd be 0, x1, and then lambda 2, x2, 0, 0, 0. As we go across into our normal multiplication, just spits out that single matrix right there. And so what we found is I can collect all the eigenvalue eigenvectors so we can write this as a single equation. A times x1, x2, up to xk is equal to x1, x2, up to xk times a special diagonal matrix of lambda 1 and lambda k with zeros. And if I want to, I could just simply call that thing capital X. I could call this thing capital X. Since that's a diagonal, I'm just going to call that D. And so this looks like this. AX equals XD. But if a times x equals x times d, another way of writing that would be to take, let's say I took, what would happen, how do I move this x in front of the d to the left-hand side? It's inverse. On the other hand, I could write it like this. A is equal to, I could take this x to the other side. How do I do that? I have to put it on the right-hand side of d as its inverse, and so that'd be x d x inverse. But the only way to move it would be as if x actually had an inverse. So x needs to be invertible, which means x needs to be non-singular. And when would a bunch of vectors be non-singular? When they're what? Linearly independent. So all of a sudden we're going to have, so what does x represent? X represents the eigenvectors. What does d represent? The eigenvalues on the diagonal. If your eigenvectors are linearly independent, then the inverse, storing them as a big matrix, is fine, and I can move it as an inverse. This process, if you could do something like this, which we can do as long as the eigenvalues and the eigenvectors are appropriate, right? I can start to move them. This is always true, right? But I can move them as long as I have linear independence. And moving those along and getting a matrix that's diagonal, if we're just focusing on those particular words, we have the following definition. We say A is diagonalizable if there is a non-singular, which means invertible, matrix X and diagonal matrix D such that A x inverse X is D. And we say X diagonalizes A. So this particular version here is called diagonalization of A. But on the other hand, this version, A is equal to a matrix times a matrix times a matrix. That's normally termed what? Factors. And so this is A factorization of A. We already have other factorizations. I just did one at the beginning of class, right? It's QR factorization. We also had the elementary operator factorization, right? We have all these factorizations that we can do. When you found inverses, you were factorizing by elementary matrices if you kept track of them. QR is another type of factorization that's useful. This particular factorization only works if A has eigenvalues and eigenvectors that meet the fact that the eigenvectors themselves are linearly independent so that the inverse can actually happen. All this line is a restatement of what does it mean to solve an eigenvalue problem. Just a different way of writing this is an eigenvalue problem. That's it. But being able to move the x is different. In the end, we'd like to find x, we'd like to find d. But what does that mean? What are the eigenvalues? What are the eigenvectors? And you just write them down.
So you say A has eigenvalues and eigenvectors, which seems like it's orthogonal, right?
No. Remember, eigenvalue, eigenvector problems are about taking this thing, taking minus lambda on the diagonal elements, finding the characteristic polynomial, setting it equal to 0, finding all the eigenvalues. Every eigenvalue goes back in. It becomes a null space question, and you find the vectors that are associated with that.
And when doesn't it have those? When doesn't it have those ones?
Well, every single problem we've done actually had solutions. So When would a characteristic polynomial not have any? No, they all do, right? Because it's a polynomial. It's a real valued polynomial. The solutions will at least be in the complex plane. So we're guaranteed it. So yeah, this always happens. Whether or not the next two rows, depends on how special x is, if it's non-singular. Now, so we have A. A can become this AX equals XD, where D is made up of the lambda 1 to lambda n eigenvalues, right? So this becomes a solve the eigenvalue vector problem for A. So we solve the eigenvalue vector problem for A. We can stuff the D's here. We can stuff the X's here, which is x1, x2, up to xn, where each of these are the associated vectors with those particular values. If this is true, this particular thing happens. Now, the question for us that we're going to be interested in is I would like to have D by itself and I would like to have A by itself, which means when does x inverse exist? So we can go to A is equal to x d x inverse, or we would have x inverse ax is equal to d. In other words, you can ask for, the person specifically is asking to write the diagonalization. So if they say write the diagonalization, they're saying they want you to write that. If they ask you for write the diagonal factorization of A, give me A as factors, they want you to write the first one. The only way I can do this is, does x inverse exist? And so the first thing, what we need, obviously, is n linearly independent xi. Because if they're linearly independent, that thing is going to be non-singular, and therefore it's invertible. So I need linear independence. So we have a couple of theorems. First, if you're given a bunch of lambda, I don't care how many you have, if you're given eigenvalues and they are distinct, there's no repeated eigenvalue. There isn't any, oh, I found, what are your eigenvalues? 1, 1, and 3. So you had 3 eigenvalues, but 1 occurred twice. Yes, that's non-distinct. So if they are distinct from each other, that will immediately give us that x1 to xk are linearly independent. So I don't even have to check the vectors. So that's kind of a nice process. So if I would go back through a problem, say for example, let's say A was equal to 1, 2, 3, 0, 1, 0, negative 1, 0, and 0, 0, 2. What is lambda 1? 1. What is lambda 2? And what is lambda 3? How did you know that was the eigenvectors value so quickly? It's diagonal, right? I'll do this all the time. If I want to make your life hard, I'll do that. And then you got to put minus lambda, minus lambda, minus lambda, take the determinant of this big ugly thing, and then if it's diagonal, read the diagonals. Okay? So that immediately tells us that we have this, right? Now, are these distinct? Yes. So if I would go back and find x1, and then find x2, and find x3, I don't even need to check these. These are going to be linearly independent. because they're distinct, these must be linearly independent. We're good. And that would tell me that A could be written as what? Obviously, in the end, if you forget the order of like who's the inverse and who's not, write it this way, right? AX equals XD. Write it exactly the way you do eigenvalues, right? A times X is X times your constant, right? That's how we work these things out. So if this is A times X equals X times a constant, therefore A is what? That, which would be whatever x1, x2, x3 times 1, 0, 0, 0 minus 1, 0, 0, 0, 2 times whatever x1, x2, x3, heck. Make it bigger. Whoops. x1, x2, x3 inverse. So you still have to find these. How would you find those? Anybody remember? I'm looking for the, once you have the lambdas, what do? You put them back into the original matrix by subtraction on the diagonal, right? And so lambda 1 was what? 1. So what am I going to do for every one of those guys? Subtract 1. Because it becomes 0, 2, 3, 0, minus 2, 0, 0, 0, 1, augmented with 0, 0, 0. Why do I augment with 0, 0, 0? I'm looking for null space, right? Who's my lead variables? There's my first non-zero. Here's my first non-zero. So who does not have a lead variable? Column 1, which means x1 is equal to an alpha, right? And this one's rather easy. This here tells me what? x3 is what? 0. And this right here, I don't even have to worry about the next one. That row right there tells me x2 is 0. And so that tells me that x1 has to be what? Something 0, 0. I don't care what that is, let's just make it a 1. So I'm going to call x1 equal to 1, 0, 0. Everybody okay with that? So we need to be able to find, go back through here and plug and subtract and figure all these things out. Sorry.
You don't care about the size, it's just that direction.
Right, it's just direction. That actually gets to, and so kind of note on this. And so on the other hand, it could have been 2, could have been 3, could have been half, right? We could pick anything we want.
Could you just wait and then throw in numbers to make your computations easier? Like, that's going to be...
Oh, like on certain ones? Like, yeah, picking certain particular x's. Sometimes you want to go through here and always pick things of length 1. And so only pick alphas that make this of length 1. So make the column... If we're interested in like stochastic processes where everything is probabilities, where each of the rows needs to eventually sum to 100%. And so this would tell me 100% of the first element, none and none. But on the other hand, what if I had a thing that was like this, 1, 0, 1, 1, 0? Then I'd rather pick 0.5, 0.50, so that way it sums to 100%. So 50%, 50%, and 0. So if it's a stochastic process, you might want to do it that way. Or we talk about probability vectors. So lambda 2 was equal to what? Minus 1? And so that would be what? 2. So it would be 2, 2, 3, 0, 0, 0, 0, 0, 3, right? Subtracting the minus 1 from each of those. Okay, there's a lead. There's a lead. Who's my free? x2 is an alpha. This is rather easy to read. So what's x3? Has to be, that's a 0. But if this is an alpha, and that's really 1, 1, right? And so this would come to the other side. What does that make x1? A negative alpha. And so what does that mean my vector looks like? My vector now looks like a minus alpha, alpha 0, which is, might as well just simply say that x2 is equal to negative 1, 1, 0. Or, again, if it was stochastic, well, now stochastic means everybody has to be positive. So might do a different length, right? What's the length of this? It'd be root 2, right? So if I wanted to, I could do a negative 1 over root 2 and 1 over root 2. And then lengthwise is now interpreted as length 1. Okay, but, we could work that out, if I wanted to. Really, it could be negative 2, 2. It could have been positive 2, negative 2. They have to be opposite signs. All right, what about lambda 3 was 2? If it's a 2, then my vector becomes minus 1, 2, 3, 0, negative 3, 0, and 0, 0, 0. So negative 1, 2, 3, 0, negative 3, 0, 0, and 0, 0, 0, 0. And so that tells me lead, free. So I could say x3 is equal to alpha, but this is easy to read. Obviously x2 is 0. But if that's a 0, he's gone, right? But that's a 3 alpha, comes over the bit, so that means x1 is equal to 3 alpha. And so that would mean that x3 is 3 alpha, 0 alpha, and if I just plug 1s in. And so obviously we could pick things like 3, 0, 1, or whatever you want. It doesn't matter. I'll pick a third, like 1 and 1/3, if you want to do it that way. Okay, now, here's the deal. So we found that A, what was A? I keep forgetting that. So there's my A. Copy, paste, is going to become x d x inverse. And so what's x? X was 1, 0, 0, negative 1, 1, 0, and 3, 0, 1 times, was it 1, negative 1, 2, 0, 0, 0, 0, 0, 0. And then I take this whole matrix here, 1, 0, 0, negative 1, 1, 0, and 3, 0, 1, and have to invert it. And then all of that multiplied would just spit that one right back out. Might not look pretty, but we'll have a reason why here in a bit.
So if you didn't have A, you'd have to be given those eigenvectors.
Right. If I give you the eigenvalues and vectors, you could write it however you want. Right. But from A, you should be able to find eigenvalues. You can find eigenvectors. But note, because the xi are not unique, that implies that x is not unique. Like I said, I could have actually, instead of this being this negative 1, 1, I could have actually made this minus 0.5 and 0.5, but that means this is minus 0.5 and 0.5. And guess what? Multiply that all out, it will still make A. Which would somewhat make sense because it's on both sides. Right? So it doesn't matter which of the scaled vectors you pick, right? As you do this, in the end, it's not unique on it. The other thing that could make this is like, not only is x not unique, d is not unique. But the question is, well, why? Because aren't the eigenvalues unique? And the answer is, well, sure. But does it matter the order I put them in? For example, A could have been written as, take my D and just switch the order. I put a 2, 0, 0, 0, 1, 0, 0, 0, minus 1. Well, then correspondingly, what am I going to do with the vectors now? Who was 2's vector? It was 3, 0, 1, so it has to go 3, 0, 1. Who was 1's vector? Well, 1's vector was 1, 0, 0, so it has to go 1, 0, 0. Who was negative 1's vector? Well, negative 1's vector was minus 1, 1, 0, and so that's minus 1, 1, 0. I can choose to put the order of the values. The values aren't specified in a particular order. There is no first eigenvalue. So as long as what's important is this eigenvalue must have its associated eigenvector of any scaling in the same spot. So there is no one answer. So you could do all your work, check it to the back of the book, and it's like, well, that doesn't look right. I mean, it's not exactly what they have. That doesn't mean you're wrong. The question is, what's the order that you wrote your eigenvalues? And then what are the vectors that you picked for those eigenvalues? Because you get to pick them. If you've done that right, and you've done your work correctly, then you're correct. It's one of those things where, what would be a check? Multiply that thing out, which would be not fun. But you could, and you should get A right back. This is also a really good example where you would throw this into a numeric system, and I bet you multiply it out, and I bet you don't get quite A.
So the question would be like, find the factorization. Because I mean, your A is always going to be the same.
Yeah, your A is always the same, right? But I'll ask you for A factorization based on this according to a particular rule. And then you can always check it by multiplying it. But on the other hand, computationally, if you would just type this into MATLAB, most likely you wouldn't get the numbers 1, 2, 3, 0, negative 1, 0, 0, 0, 2. You'd probably get things like 1.000, and the 0 might be 10 to the negative 16th. Because there's probably error that's going to occur, especially on that operator. This operator is probably going to have error. If you do it by hand, there's obviously no error. You just keep it all exact. But a numeric system will immediately start approximating. And this is where the oops are going to help show up, usually. So, any questions on what I just did? The fact that they aren't all unique. All we're looking for, again, this isn't really anything new. Do you know how to find eigenvalues? Do you know how to find eigenvectors once you know the eigenvalues? All it's saying is, now that you've done that, stuff them in this. Just put them in the right spots. That's all you have to do. Just put them in the right spots. And now comes the question. Yep?
Why are they not unique?
They're not unique because these columns can be rearranged. But if I rearrange those columns, I just simply rearrange those. But those are different vectors. Sorry, different matrices. Like, for example, is this matrix equal to that matrix? No. They're based on the same idea, but they're not the exact equal matrix. So you have a few tweaking arrangements that you can do. And there's
you don't mean distinct.
I mean unique, I mean exactly one matrix at all. A unique matrix means it's this order of numbers and only this order of numbers with no rearrangement at all. That's what uniqueness means. The eigenvalues are unique. How you write them in this collective thing, you have freedom.
So for the other factorization, you said you'd use it like when it's overdetermined, but what you use.
Right, yeah, QR factorization is useful for solving systems of equations.
And then when would this one be useful?
Okay, so the big question. Why? Why do I care that A times X is equal to X times D? Or again, A is equal to XD, X inverse, or X inverse A, X equals D. Why in the world are we, interested in this particular stuff? Well, actually, can I pause on this one? I guess one thing I didn't mention, which will be important. Whoops. I hit the wrong thing. Undo. Yes, the non-distinct. In other words, now comes the question of what if the lambda I are not distinct? To do this, then we have to go ahead and check that the x of I are linearly independent. So an example of something like that. Let's say I'm going to do two matrices side by side. A is equal to 1, 0, and 1, and 0, 2, 0, and 0, 0, 1. And let's say B is equal to a 1, 1, minus 1, a 0, 2, minus 1, and a 0, 0, 1. What is lambda 1? 1. And then what is lambda 2? What is lambda 3? 1. So we normally just don't write that. So 1 occurs twice. What's lambda 1? 1. What is lambda 2? It's 2. So both of these have, but 1 occurs twice. So I only have 2 eigenvalues. And so what do is we look for the vectors. And so I'm going to look for so lambda 2 is equal to 2. So we're going to augment this. If I subtract the 1s, that's 0, 0, 1, 0, 1, 0, 0, 0, 0, augmented with 0, 0, 0. And do this subtraction, that's minus 1, 0, 1, 0, 0, 0, and 0, 0, minus 1, augmented with 0, 0, 0. So I just subtract the 1s. Okay, who's my leads? There's my leads. So who's my free? x1 equals alpha, but for both of those, x2 is 0, x3 is 0, right? So x2 is 0, x3 is 0. So what's my vector? 1, 0, 0. All right, and what would be x2? So for here, this is my free. x2 is equal to alpha. But what from this, x3 is 0, but if x3 is 0, what's x1? And so what is x2? 0, 1, 0. So now what would this thing look like? This would look like A, right? A times x, but what's x? All right, we would look at this and is equal to x and then d. And what's d? D is 1, 0, 0, 0, 2, 0, 0, 0, 1, right? 1's occurred twice. Whose 1's? It's 1, 0, 0. Whose 2's? 0, 1, 0. Whose 1's? 1, 0, 0. Is this thing invertible? Look at that. Are the columns linearly independent? No. And so doesn't exist. Look at it this way. I mean, just it shows up. One column occurs many times. So x inverse does not exist. And so what was A? A was 1, 0, 0, 0, 2, 0, 1, 0, 1. And we could actually check that out. That's 1, 0, 0, then 0, 2, 0. You could take this and multiply those two, and you get the same thing if you want to write it out that way. But anyways. But there's no way for me to move the x. All right, on the other hand, if I look at it this way, what is lambda 1? It's going to be 0, 1, minus 1, 0, 1, minus 1, and 0, 0, 0, augmented with 0, 0, 0. All right, but those two are equal, So when I subtract the 2, this is actually 0, 0. So what's my lead? Him. Who's my free? I have x1 is alpha and x3 is beta. And so what does that make x2? Sorry. This is a negative beta, comes over there. That's also a beta. So what do I get? I get alpha, beta, beta. But how do I write that? That's alpha times 1, 0, 0 plus beta times 0, 1, 1. How many vectors does this guy have? 2. So if one of the times it occurs, we would pick the first. The second time it occurs, I'd pick the second. And so what we would say is, oh, lambda 1 equal to 1 has x1 equal to 1, 0, 0, and lambda 3 equal to 1 has x3, which is equal to 0, 1, 1. And we'll have lambda 2 equal to 2 has x2 equal to whatever it is. So this one has independence, because what happens is, what you'll notice is, if you have a multiple occurrence of the eigenvalue, if it occurs twice, you better get 2 vectors. And if you get those 2 vectors, then this thing will, but then x inverse will exist. And so then we're good to go.
So if you have 3 indistinct eigenvalues, you need 3 variables for that.
Yes. Somehow that problem's going to have to end up to have the number of free variables as you have occurrences. And if that's true, then x is going to be invertible. So for this, x inverse exists. And so we can go ahead and do the problem like we want. If this happens, right, if x inverse does not exist, we call matrix A defective. Which is going to occur when you have multiple roots, right? You have eigenvalues that are non-distinct, and you don't get enough eigenvectors that are independent. And if that's true, your original matrix is called defective. Okay. Back to the question that was asked. Why? Why is AX equals XD becoming this whole A is equal to XD, X inverse, or X inverse AX is equal to D? In particular, we're interested in is the diagonal factorization. Why are we interested in these particular types of problems? And the reason, one in particular, is this: if A is used many times. And so for the example is a Markov chain. We've already done our Markov chains, right? Anybody remember why we were interested in Markov chains? We were looking for special bases that were the what? What happens if you, right, when we go back here on a Markov chain, Markov chains had this special process where we had this AX is equal to, and if it ended up being a lambda x, the eigenvalue eigenvectors were a natural basis because they do the what? They're stretching. So the idea of a Markov chain says, I start off with vector 0. Then vector 1 is simply A times vector 0. And then vector 2 is A times vector 1. And then we keep going. Vector k is A times vector k minus 1. But if I look at this, A times vector 1 is really A squared of vector 0, right? Because there's A times. I could take V1 and replace it by that, and that becomes AA, and that becomes A squared, which means vector k becomes AK vector 0. So I keep multiplying by A. And if I keep multiplying by A in terms of Markov chains, these the V0, V1, up to Vn are the state vectors which form the Markov chain. This whole Vk is equal to AK V naught. Doing this over and over again was our Markov process. A itself is normally called a transition matrix. The examples that we did on this before would be like, there's so many people that live in the city, there's so many people that live in the suburb, and there's a moving process going on. 80% stay, 20% go. And then 30% leave from one, 70% go. And so there's this flowing back and process. There's this thing that happens year after year. You multiply by this matrix, people move. You multiply this matrix, people move. And doing this transition moment after moment was this entire process. And it ends up being that this process is dependent upon A to the K, where you get the next state vector forming the Markov chain. This entire process is occurring over and over and over again. But on the other hand, A to the K, if A is equal to this XD X inverse like that, so let's say X has eigenvalues and eigenvectors, which we used before as a natural basis. It's the stretching guys, except now I'm going to write it as a factorization. What would A to the K look like? Well, that would be just simply XD X inverse to the K. But that's just XD X inverse times XD X inverse times XD X inverse. Well, how does that look any better? Well, what is an X inverse X? And then X inverse X, and X inverse X. Everybody between this D and this D, every X is going to become what? The identity. And then what do I have? A bunch of D's. How many D's do you have? K of them. And so this has become X D to the K X inverse. But D is a diagonal matrix. And diagonal matrices, when you raise them to powers, you just put that power right on the elements themselves. And so that means A to the K is simply X times lambda 1 to the K, lambda 2 to the K, lambda n to the K, everybody else is 0, and then X inverse. So what happened to the K? The K only goes to the eigenvalues. No one else matters. But the eigenvectors are still in the problem, but they only occur once at the end and once at the beginning. But the multiplicity, I keep applying the transition matrix. What you're applying is the eigenvalue, the eigenvalue, the eigenvalue keeps getting multiplied by K. The other eigenvectors don't even change. They just stay put. So what does that look like on my process now? So if I wanted to do things like, okay, I could say, the long way of something like this, if without this diagonalization, without XD X inverse, A to the K times a vector, let's say this is called X naught. How would you do that? You would have to do A times X naught. Multiply by A, 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 and that finally becomes XK, the next state vector. What about with a diagonalization? You found the eigenvalues and you found their eigenvectors. That would tell me that my XK is, all right, these X's are different, sorry. This capital X are the eigenvalues times lambda 1 to the k, lambda n to the k, 0, 0, times x inverse times, I shouldn't have picked x. Let's make this b. vk, v naught.
So calculate with eigenvalues or eigenvectors.
Yeah, this is the eigenvectors. This is the eigenvectors, and this is the eigenvalues, all raised to the kth power. But an eigenvalue is just a number, right? I can take a number to the kth power. Well, you kind of look at it and say, like, well, isn't that kind of odd? Well, how do you take an inverse of a matrix times a vector? I could take that matrix, I could find its inverse, and then I can multiply it. Or what could you do? You could augment it with it and then do the same work, right? And then you would immediately get that vector out on the other side. Anybody? So if we would call x inverse v naught, let's just simply call this w. How do I find it? What you would do is you would take x, you would augment it with v naught, you would do row ops until you get the identity, and then on this side would be w. That's the fastest way to do it. Everybody remember that? But w is made up of w1, w2, up to wn. So we would do that, but that's just a straightforward row operation. So really what's happening is this vector is being multiplied by something, and it comes out as a nice clean vector. How do I find that nice clean vector? Just use row operations to do it. All right, so, okay, what does that mean about your next guy? Your next guy is equal to x times lambda 1 to the k, lambda n to the k, 0, 0, and then times a w1, w2, down to wn, right? Where these are that's how you found those w's. Well, that's a bunch of zeros. So when I multiply this matrix like that, that's just going to be x. If I go ahead and multiply this, this would be just a nice vector that looks like this. Lambda 1 to the k, w1. Lambda 2 to the k, w2. Lambda n to the k, wn. What happened to everybody else? They're all zeros. It's just simply the first row gets the first. So the first row gets the first eigenvalue. The second row gets the second eigenvalue. The third row gets the third. Well, why isn't it on the other ones? Because it's a diagonal matrix. Everybody else is zeros. Well, how do I take a matrix and multiply it by a column? Same way we all know how to do this. And so what this will be is this could be considered, right, this x could be thought of as a row, which is what? Eigenvector 1, eigenvector 2, eigenvector n is equal to vk. But a row times a column is a scalar product. And so what this is vk is simply lambda 1k w1 times x1, which is a column, plus lambda 2k w2 times x2 plus lambda nk wn xn. So what do I have? Number, 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 vector, vector, vector. It's a linear combination of the eigenvectors. How much do you get? Well, how much are those? Who's the only guy that changes? So for this, the w's you could find once, right? Just go ahead and do this augmented matrix. You find your w's. What are your lambdas? Your lambdas, you already found them. What are your x's? Those are the eigenvalues. You already found them. And so what is the only thing that changes in this entire Markov process? What is the only thing that changes from V0 to V1 to V2? What's the only thing that changes throughout this entire thing? The power on those lambdas. That's the only thing that's going to change in the entire system. It's a linear combination. Now you can start to interpret. What happens if these lambdas are less than 1? Let's say between -1 and 1. You start taking higher and higher powers. What does that go to? It goes to 0. What if any of these lambdas are larger than 1? It goes to infinity. What if all of them are less than 1, but one of them is exactly 1?
Then it will go to that one.
Everybody else goes to 0, and it becomes literally that 1, which means that there's only one eigendirection that even matters. It just simply stretches along that, and so everybody goes to that. And so it ends up being that, sure, I can multiply by a bunch of times, but if I do a little bit of work beforehand, the only thing that matters is the eigenvalue powers, and we can use that to interpret the process. In next class, we'll do this for a few and start to interpret the process. All right, that's it.